Good morning, students. In the last class, we have covered the set chapter definition and representation of sets and its examples and types of sets. In this lectures, we are going to study the next types of sets. Now, first one is equal set. First one is equal set. The name itself indicates equal. When we can say sets are equal, two sets A and B, two sets A and B are said to be equal, written as A is equals to B if every element of A is in B and every element of B in A. Simply we can say two sets. Let us consider two sets. Capital A and capital B are the two sets where every element of A should be in set B, whereas every element of B is in A, right? Now, the next definition is equivalent sets. When we can say equivalent sets, two finite sets A and B are said to be equivalent if n of A equals to n of B. That is, n stands for number of elements present in set A is equals to number of elements present in B irrespective of their order, right? Now, in the next, some important note, equal set are equivalent, but equivalent sets need not be equal. What? Equal sets are equivalent, but equivalent set need not be equal. For example, let us consider set A equals to 4, 5, 3, 2 and set B equals to 1, 6, 8, 9 are equivalent but are not equal. Yes? Clear? The equal set, what we are said here, in an equal set, two sets A and B are said to be equal if every element of A is in B and every element of B is in A. In this example, first set A consists 4, 5, 3, 2, but in the set B 1, 6, 8, 9. 1, 6, 8, 9. Here the elements are different. So, equal sets are equivalent, but equivalent set need not be equal, right? Now we move to the next slide. That is nothing but subsets. Sub means here the branch, right? The meaning is sub means a branch. Now we see what is subset. Let us see. Definition of a subset. Let A and B be two sets if every element of A is an element of B. Then A is called subset of B. And we write it as in this way. A subset B or B superset A, and it is read it as A is contained in B or B contains A. That is, B is called superset of A, right? B is called this term. B is called superset of A is called subset of B, right? Some important points are here. We see one by one. In the first point, if A is a subset of B and A is not equals to B, then we write A subset B or B superset A. Read as A is proper subset of B and B is proper superset of A, right? If A is subset and equal to B and A is not equals to B, then we write A subset B or B superset A, and it is read as A is a proper subset of B or B is proper subset of A. Now second point, every set is a subset and a superset of itself. Already you know well, every set is subset of itself, right? And third point, if A is not a subset of B, then we write it as A is not a subset of B, right? If A is not a subset of B, then we write symbolically it as A is not a subset of B. Now move to the next point. The empty set is a subset of every set. These are the two important notes. The empty set is subset of every set, right? And the next final point is, if A is a set with n of A equals to m, then the number of subsets of A are 2 to the power m and the number of proper subset of A are 2 to the power m minus 1, right? If a set with m numbers, then the number of subset of A are 2 to the power of m and the number of proper subset of A are 2 to the power of m minus 1, right? Now we move to the next slide. That is nothing but an example of subset, right? See here. For example, let us consider, let A equals to 3, 4. Then the subset of A are 5, 3, 4, 3, 4. Here n of A is 2. A consists number of element is 2 here, that is 3, 4, and the number of subsets of A is, if it consists 2 elements in it, then the formula, as we know, 2 to the power of m is the standard formula for finding subsets, right? Here n of A is 2 elements, then we can write it as A equals to 2 to the power of 2, then which is equals to 4. That is nothing but 5 is first subset, 3 is second, 4 is third, and every set is subset of itself, that is 3, 4. Again here we have to remember 5 is, that is empty set is subset of every set and every set is subset of itself, right? Also 3 is a subset of 3, 4 and 2, 3 is not a subset of 3, 4 because 2 does not exist in the set or you can say subset 3, 4, right? Now next we move to power set definition. The power set, the set of all subsets of a given set A is called power set. The set of all subsets of a given set, what we are saying here, all subsets of a given set A is called power set of A and is denoted by P of A, right? For example, if A equals to 1, 2, 3, then P of A is nothing but all the subsets of a given set A. See here, the power set P of A equals to, first initially we write empty set is subset of every set, first one. Now 1, 2, 3, 1, 2, 1, 3, 2, 3, and every set is subset of itself, that is 1, 2, 3. Clearly, if A has n elements, then its power set P of A contains exactly 2 to the power of n elements, right? Exactly 2 to the power of n elements, right? Next we move to the next slide. Here some tricks for problem solving. Let us consider the number of elements in the power set of power is the number of element in P of phi is 4, or the cardinal number of power set, that is P of phi is what? 4. Since, let us see how it is equals to 4. Since P of phi equals to what? Every set is subset of itself, right? That is P of phi equals to phi. Next, power set of P of phi. Already phi is there. Again P of phi is nothing but one more phi we add here. And next, P of phi, which is nothing but phi and phi comma phi. Therefore 1, 2, 3, 4 are nothing but the cardinal number of the given set is nothing but 4, right? Now we move to Venn diagram. Already you know well Venn diagrams. To express the relationship among sets, we represent them pictorially by means of diagram is known as Euler-Venn diagram, or simply Venn diagram, right? In a Venn diagram, the universal set U is represented by a rectangular region and its subsets are represented by a closed bounded circle, right? And its subsets are represented by closed bounded circles inside this rectangular region, right? We will see in the next slide its operations on sets. Let us consider first one, union of two sets. When we can say union of two sets, the union of two sets A and B written as the union of set A and B are written as A union B, and it read as A union B is a set consisting of all the elements which are either in A or in B or in both. It is important here, union of two sets. Either it may be present in set A or set B or in both. We can write it in the standard form. A union B, which is equals to, here x is a variable, x such that x belongs to A or x belongs to B, right? For example, if consider if A equals to A, B, C, D and B equals to C, D, E, F, then A union B equals to A, B, C, D, and already C, D is common here. We do not repeat this term, we write only once here. A, B in the first term and C, D is a common term, again we write it as only once, and E, F. Either the elements are in A or in B or in both, right? Here A, B, C, D, E, F is nothing but union of two sets, that is nothing but A union B, right? Now A union B. Now in the next slide we see the diagram See here, the set, it is nothing but set A, it is denoted by A, and set B, right? It is set B. Usually the universal set is denoted by a rectangular, it is nothing but U, and its subsets are denoted by circles inside the rectangular. Here the shaded region is there, which is nothing but union of two sets, right? Union of two sets. Now we move to next, intersection of two sets. The intersection of two sets A and B is written as A intersection B, and it is read it as A intersection B is a set consisting of all the common elements of A and B. Then we write it as A intersection B, which is equals to X such that X belongs to A and here, and X belongs to B. But in the union set we write it as OR here, right? But in the intersection we write AND, right? We write AND, that is A intersection B is the element belongs to A and element belongs to B. For example, if A consisting of A, B, C, D, and set B consisting of C, D, E, F, then we write the intersection of A and B is nothing but C, D. Here the simple logic is the common elements between A and B, right? The common elements between A and B. See the diagram, Venn diagram for intersection of two sets. Venn diagram for intersection of two sets. Here again, U is the universal set. U is the universal set. Again, its subsets are denoted by the circles A and B. Here the common, the shaded region is this much. This is the shaded region, that is A intersection B, the common region between set A and set B, right? Now we move to the next slide. Disjoint set. Disjoint sets is nothing but two sets A and B are said to be disjoint if A intersection B equals to 5. There is no common element. Simply we can say A and B have no element in common, right? For example, if A equals to 1, 2, 5 and B equals to 2, 4, 6, then A intersection B equals to what? 5. There is no common element between set A and set B. Therefore, we call it as disjoint set. If we see the Venn diagram, here there is no common region between set A and set B, right? They are far away from each other. There is no contact or there is no common element between A and B, right? Therefore, we call it as disjoint of a set. Next definition is difference of two sets. If A and B are two sets, then their difference is nothing but A difference B is defined as X such that X equals to or X belongs to A and X does not belongs to B. Difference of two set is nothing but the element belongs to the set A but not set B. The element belongs to set A but not set B, right? We see similarly B difference A. In this case, X such that X belongs to B and X does not belongs to A. Here the element belongs to set B but not set A. For example, if A equals to 1, 2, 3, 4, 5 and set B equals to 1, 3, 5, 7, 9, then A difference B is, here A difference B is nothing but this element which belongs to set A but not set B. The element should be belongs to set A. The element must be in set A but not in set B, right? Let's see which elements are present in set A. Only 2, 4 are the elements which are present in A, and the remaining 1, 3, 5 are common in set B also. Therefore, we take only 2, 4. And similarly, B difference A. Similarly, B difference A, that is the element belongs to set B but not A. Here we get only 7 and 9. There is no 7 and 9 in the set A. Therefore, B difference A is nothing but 7, 9. See, here Venn diagram also is there. For A difference B, the element belongs to only, the shaded region indicates the element which are in set A only but not in set B, right? Or not in common also. And similarly for B difference A, the element belongs to set B only but not in common as well as set A, right? Now we move to the next slide, symmetric difference of two sets. Here the symmetric difference of two sets A and B is denoted by symmetric A triangle B is nothing but symmetric difference of two sets A and B. It is A symmetric difference B is equals to A difference B union B difference A. For example, if A equals to 1, 2, 3, 4 and B equals to 1, 3, 5, 7, 9, then A symmetric difference B, which is nothing but A difference B union of B difference A. Now A difference B is nothing but the element belongs to set A but not set B, that is nothing but 2, 4 union symbol as it is. Again here set B difference A, the element belongs to set B only but not A. Here 7, 9 is only the element which are present in B but not in A. Therefore, the union of these two sets can be written as 2, 4, 7, 9, right? If we see in the Venn diagram, it is clearly defined here 2, 4, the shaded region. Set A consists 2, 4 and set B consists 7, 9. There is no common elements, right? This region is not considered. Only 2, 4, 7, 9, right? Now we move to next slide, that is complement of a set. Last definition of this chapter, sets. If U is a universal set, yes, if U is the universal set and A is a subset of U, then the complement of A is a set which contains those elements of U which are not contained in A, and it is denoted by A dash or A to the power C. Thus A dash, or you can say complement of a set A, is equals to X such that X belongs to U and X does not belongs to A. Then see in the Venn diagram, for example, if U equals to 1, 2, 3, 4 and A equals to 2, 4, 6, 8, then A dash can be written as, or you can say the complement of A is nothing but A dash, right? Universal set consisting set of natural numbers, that is 1, 2, 3, 4 so on, whereas set A consisting even natural number. Therefore, A dash is nothing but odd natural numbers, that is nothing but A dash. The element belongs to U but not A, right? Here some note are there. U dash equals to phi dash equals to u, and A union A dash equals to u, and intersection A dash equals to phi, right? Thank you.